We're going to be talking about safety integrity level, or SIL, understanding the how, the why, and the what. So audio is provided via the internet, so enable your speakers and mute your microphones, please. Once again, please make sure your mics are muted. There is a question and answer tab on the side of your screen, and go ahead and type in questions. I will try and check periodically throughout the webinar and answer the questions as they come up. Or if I don't see questions during the webinar, I'll take some time afterwards to answer them. One thing that I think we're going to try is I will get the questions and send them out to the list of people who signed up for the webinars, because if you have the question, probably others do too, and not everybody is able to make the webinar. So I think we're going to go ahead and try to do that this week. Also, a recording of the webinar is going to be posted on the exida website and also our exida Academy YouTube station. And everyone that signed up for the webinar will be getting a copy of the slides later this week. So today we're going to be talking about SIL and the SIL rating. So many end users are requesting certificates for their products that they buy to reduce liability and risk. Manufacturers, if they haven't already, are trying to stay ahead of their requests by certifying their products. The certification process is a thorough process and provides instant recognition of the product reliability, safety, and security. During the certification process, a manufacturer may have a requirement to certify their product to a certain safety integrity level rating, and that's what we're going to talk about. This webinar is going to discover what it means for the manufacturer, what is SIL capability, how to calculate SIL, how to reach a certain SIL rating, and is there any way to improve your SIL rating. I'm Loren Stewart. I'm a CFSP. I graduated from Virginia Tech with a BS and ME. I started working in custom design and manufacturing, and now I work for exida as a mechanical engineer, safety engineer. So I help with all of our mechanical customers, along with certifying products and doing FAMIDAs. I also am doing research and working on our 2H initiative. So who is exida? We were founded in 1999, and we have offices all over the world. So wherever you are or your customers are, we have an office close by. We are divided up into 4 main industry focuses: the OEM, system designer, end user, and engineering contractor. We have support in every one of the industry focuses, along with tools to help the support. We have main products and service categories that we're going to chat about real quick. We have consulting, which we will talk about more today, especially the IEC 61508 and 511 process safety consulting. We also have consulting in alarm management and control system security. We have a bunch of engineering tools, Excellentia, which I will be doing an Excellentia demonstration today, along with Safety Case, our FAMIDA tool, and alarm rationalization. We have product certification, which is for functional safety 61508, and we're going to be talking about that a lot today, along with control system cybersecurity network and network robustness. We also do a bunch of trainings. You can come to us, we can come to you, however you want. Anything functional safety related, we can teach you. We also have a bunch of reference materials. We have our databases, our tutorials, textbooks, reference books, market studies. And finally, we have professional certification. We have our CFSE and our CFSP programs. So whether it's process, products, or people, as long as it deals with functional safety, we have you covered. A little bit about our products. Like I said, today we're going to take a look at Excellentia and what you can discover through that. We also have our PHA program. We have our SERH viewer, our SIL alarm program, and our SIL stat program. And we like to brag a little bit that exida has authored the most industry references for automation, safety, and reliability. We have authored industry data handbook on equipment failure data and the most comprehensive book on functional safety on the market. So getting back to topic why you really came here today is safety integrity levels. What are we going to talk about? We're going to say what really happens in an exida certification, so you get the background of the certification process and how to achieve the SIL level, how to find a safety integrity level, how is the SIL rating used, what this means for a manufacturer, what is SIL capability, how to calculate a SIL rating, how to reach a certain rating, and is there a way to improve your SIL rating. So we're going to get started in what happens in an exida certification. I'm going to give you the very, very, very condensed version because we have a lot to talk about today. But we start off each certification process with a kickoff meeting. These are usually done via a web meeting, but we also sometimes hold it on site. We talk about what is expected on both parts and how we're going to achieve this. Next is we perform FMEDA analysis on the product. And we take apart each product and break it down per component to find out each way each part can break and give you both your dangerous failure rate and your safe failure rates from it. Next, we create a proven in use analysis. This takes into consideration how long the product has been on the market. This doesn't mean that new products can't be certified. They can, but they would just go a different route, not proven in use. For the proven in use analysis, we take the shipment data and the field failures and returns data and find out just what your proven in use record is. Next, we look at a process analysis and we go ahead and make a baseline safety case. We take your quality management system and your process analysis and compare that to IEC 61508. In the standard, there are different qualifications needed to be reached to be IEC 61508 qualified. We go through each of these recommendations or requirements, each of these requirements, and make sure that you are meeting each. From there, we make an action item list or a gap list, and we show you where you are not meeting 61508. Then we do an on-site audit. At this on-site audit, we look at if you're actually doing exactly what you're saying you're doing through your processes. Then we also clean up any gaps or action items that might be left over and finish the safety case out. Once the safety case is finished, we have a second auditor come through and do a certification audit and make sure that the first auditor did not miss anything. So it's a very thorough process. Once you are done, you receive a certificate. This certificate shows your SIL capability level, what type of element or device you are, along with a hardware fault tolerance, and there's a lot of information on this. We actually just did a webinar last month on how to decipher this certificate. But the main point we want you to understand today is that just because the certificate says SIL 3 capable, that does not mean that you just take this and can be used, this product can be used in any SIL 3 system. There are restrictions. You have to make sure that the safety function is the exact safety function that this product was designed for, and many other things. And we're going to go through what these restrictions are today. So how do you find a safety integrity level? The SIL level of a product is determined by 3 things. First of all, you have your systematic capability rating, which what you just saw on the certificate, which said SIL 3 capable. Secondly, you have your architectural constraints for the element. And third, you have your PFD calculation for your product. I'm going to go ahead and break apart each of these categories so you know exactly what we're talking about when we talk about the systematic capability or whatnot. So to, I guess, drive the point home is this little picture. To be compliant, you have to be in this tiny triangle in the middle of all 3 of these circles. You have to be compliant in the SIL capability and in the architectural constraints and in the probability of failure. You cannot just meet 1 or 2 of these and say you're compliant. You have to be in that sweet spot and meet all 3 of these to actually have compliance and be that SIL that you're talking about. And a lot of people don't realize that. They just take the SIL capability or the architectural constraints or the probability of failure and assume that that's the one and only piece of information that they need to be compliant. But it's not a pick and choose off a list. You have to have all 3 to be able to do so. And I'll explain a lot more why. So the first thing we're going to look at is the top of the circle, or the systematic capability. And systematic capability is established by having your quality management system audited per IEC 61508. So if your quality management system meets the requirements, a SIL capability rating is issued. So once again, you see on the certificate it says SIL 3 capable. This rating is achieved depends on the effectiveness of your quality management system. The certificate is for the systematic capability of your product. Next, we're going to look at the architectural constraints. And architectural constraints are established by following Route 1H or Route 2H, which is explained throughout 61508. Route 1H involves calculating the safe failure fraction for an element. And just for an example, a valve is typically one component of the final element for a safety instrumented function. To continue this, the safe failure fraction must be calculated for all components of the final element, not just per se a valve. So, for example, a final element of a cyst may consist of a solenoid, an actuator, and a valve. So to calculate the safe failure fraction for the element, you would take the safe failures divided by the total failures for the element. Before the release of IEC 61508 2010 version, we have the 2000 version. of the standard, which allowed all no-effect failures to be considered as safe failures for the purpose of calculating the safe failure fraction. Typically, a final element would have a safe failure fraction greater than 60, which would meet the architectural constraints of SIL 2. But now, with the 2010 version of 61508, it does not allow you to include the no-effect failures with the safe failures anymore. So, for example, a valve in a close-to-trip application, there are no safe failures. That is to say that there's no failures that will cause the valve to close on its own. So even if the safe failures of the actuator and the solenoid are included in the safe failure fraction calculation, the typical safe failure fraction for a final element is considerably less than 60%, which is only good for SIL 1. So for a final element to achieve the architectural constraints of SIL 2 or higher, a hardware fault tolerance, or an HFT, of 1 must be used. So this means that you would have to use redundant valve assemblies. Or, because of the 2010 version, it now allows a second route, or route 2H, to be considered. The 2H approach involves collection of failure data, and that failure data meets the requirements of 61508, then route 2H can be used to establish the architectural constraints. And this means that it's possible for a final element to meet the architectural constraint of a SIL 2 with a hardware fault tolerance equal to 0. So you can use a final element assembly that meets the requirements of 2H in a SIL 2 system if the systematic capability and the PDF average calculation also meets the SIL 2 level. And these are the tables directly from the standard. So this kind of gives you a visual of what we're talking about. And this is for a type A product, which we'll discuss a little bit later. But this shows you that if you have a safe failure fraction between 60 and 90%, normally a hardware fault tolerance of 0 can get you to the SIL 2 rating. But now, because the safe failure fraction is found differently, you might be less than 60%. So you could only be a SIL 1 with a hardware fault tolerance of 0. Or if you go to a hardware fault tolerance of 1, you could meet SIL 2. And this is explaining the 2H table. So this is, again, for type A low demand applications. You have SIL 2, you can be at hardware fault tolerance of 0, or SIL 3 can be at hardware fault tolerance of 1. For type B applications, elements using route 2H shall have a diagnostic coverage not less than 60, and that's right in the standard. So finally, we're going to look at the PFD average calculation and how that is found. The PFD average is based on the dangerous failure rate, system diagnostics, proof test coverage, test intervals, and a few other things. Typically, a final element assembly will have a PFD average that only meets SIL 1. However, there are things that can be done with diagnostics and the proof test that would improve the PFD average to SIL 2. And we'll show examples of this and talk about how you can do this later on. But first, we're going to dive down a little deeper into safety integrity level itself and find out how it's used, why you need it. So the safety integrity level can be used in 4 ways: to establish risk reduction requirements, to look at probabilistic limits for hardware random failures, to look at architectural constraints. We just talked about that a little bit to find your SIL level, or if you have a SIL requirement that you already know you need, you can establish your architectural constraints. So it's back and forth. and to establish systematic capability. Once again, you can go back and forth, either pick your SIL level or pick your systematic capability. So first we're going to look at establishing risk reduction. To fully understand risk reduction, we're going to look at an example of a calculation. So you have a PHA and it determines that a specific hazard can occur once every 10 years, causing a major release of toxic fumes into the atmosphere. So you're going to want to determine the risk reduction factor for that hazard to occur only once in every 500 years. So it's a simple calculation. Your risk reduction factor would have to be 50. So you take that number and go to the table found in 61508. So looking at this, you have a risk reduction of 50. You come over to the table and it's between 100 to 10. So you would fall in the SIL 1 category. So for each safety function, it has a requirement to reduce risk. So the SIL level is an order of magnitude of the level of risk reduction required. So if you want to be up in SIL 2, you're going to have to have a better risk reduction factor than the 50 that you just calculated. The next section is to set probabilistic limits for hardware random failures. So we're going to look at pretty much the same chart, but this is the safety integrity level on the left, and on the right you have the probability of failure on demand, or the PFD average, which we talked about earlier. So if you calculate the probability of failure on demand to be 5 times 10 to the negative 2, you would see that that falls in to the SIL 1 level because it's over negative 2, or 10 to the negative 2. So you would have to go through this chart and find where you fall, or you can find where you fall and decide which SIL level you would like. As we talked about a little earlier, you look at 4 main things to determine the PFD average: the dangerous undetected failure rates, which you receive from the FMIDA, the proof test coverage, the proof test interval, and the mission time. And these are all factors into the equation below. You also should consider random versus systematic faults, and to understand these, it's best to have a formal definition. A random fault is a failure occurring at random times which results from one or more degenerated mechanisms. A systematic fault is a little more complex. It's a failure related in a deterministic way to a certain cause, which can only be eliminated by a modification of the design or of the manufacturing process, operational procedures, documentation, or other relevant factors. If you take this flowchart, you can see that you have a specification of requirements, design, and implementation. You can break off. If you have a systematic fault, you will result in an improperly designed system. The system is not correct. You're going to have a failure. If you look at random failures, you might have a really well-designed system. The system is correct. Great. So you go down, but you still have a random failure. So the system is no longer correct. Both random and systematic faults or failures result in the system having a failure. So why does this happen? The concept behind a failure is that a failure occurs when some stress level exceeds the associated strength level of the component. Stresses come from a number of things. So think about a failure that you've experienced. What were some of the stress factors? It could be a number of things. Over on the right-hand side, you have a list of things that could be considered stressors. It could be anything from vibration, miscalibration, maintenance errors. A number of things could stress the system. And when a system is stressed, you have to find where it's going to fall on the strength. So this is where this chart comes in. Stresses and strengths vary. They both vary with time. So strength also varies between units manufactured. So it's very hard to accurately understand all the variables involved in stress and strength, but they can be represented by probability density functions. So the failures occur when the stress is greater than the strength, represented graphically by this little section here in red. So it would be great that if strong products operated forever, but that's not necessarily the case. Unfortunately, strength tends to decrease more with operating time. So at some point in time, strength is going to decrease rapidly, and the failure rate is going to increase rapidly. And where this, at that point of time where the strength is rapidly decreasing, we call that wear out. And once again, you could see that in the little red triangle. So this failure rate plot is called a bathtub curve. In the beginning of the curve, it's called infant mortality. And as you can see, it's steep failure rate. Next, in the green section, in the middle of the curve, it's called useful life, and this is where you're going to get all of your random failures, but the good portion of your lifetime. And then at the end of the bathtub curve is called wear out, and this is when strength declines, and as you can see, that happens rapidly. The failure rate increases significantly. So the assumption of a constant failure rate is often made to simplify math used in reliability and safety calculations. This is reasonably valid for the useful life period. This assumption is actually conservative, as the failure rate of the collection of products tends to decrease during the useful life slightly, as you can see on the bathtub curve. But this assumption is not conservative if the product is used during the wear out portion and the end of the life. So one of the terms that we're going to talk about, and we already talked about a little bit, is low demand mode. And this is where the frequency, per the standards definition, where the frequency of demand of operation made on a safety-related system is no greater than once per year and no greater than twice per proof test frequency. And if the ratio of diagnostics tests demand rate exceeds 100, then the subsystem can be treated as low demand mode. The diagnostic test interval will need to be considered directly in reliability model if it is not at least an order of magnitude less than the expected demand rate. So that all comes directly from the standard. Exida kind of condensed and simplified the definition to say a dangerous condition or a demand that occurs infrequently and at least two times less often than the manual proof testing. So therefore, the proof test can be given credit for a risk reduction. So here are the charts again from IEC 61508. Now, as you can see, This is for a low demand mode operation, and the PFD average for low demand. If it is a high demand mode, the PFD average actually goes to the probability of failure, dangerous failures per hour. So if this is high or continuous mode of operation, you would use this chart instead. And the last thing that we have to consider for this is common cause. And that's definition is the failure of one or more units in a redundant system due to a common stress. So once again, we have some examples of stresses. So you could have vibration that would take out one or more of the systems, or two or more of the units in the redundant system. Or if an electrical surge took out both of the if an electrical surge would take out both, that would be considered a common cause. Now we're going to look at architectural constraints briefly again, because once again, you can go forward and back. You have your architectural constraints. You can find what SIL level you meet, or if you already have your SIL level that you need to meet, you can calculate your architectural constraints needed. So as we talked about, you're going to be looking at both type A and type B. Type A products are defined as a subsystem that can be regarded as type A if, for the components required to achieve the safety function, the failure modes of all constituent components are well defined, and the behavior of the subsystem under fault conditions can be completely determined, and there is sufficient dependable failure data from field experiences to show that the claimed rates for the failures detected and undetected dangerous failures are met. That's kind of a mouthful, and they basically say type B is everything else. So just for an example, solenoids and pressure switches are simple devices that are IEC 61508 defines as type A devices. Therefore, looking at the chart, a safe failure fraction with 0% with no redundancy, so hardware fault tolerance of equal to 0, meets SIL 1. Unfortunately, say for you were looking for SIL 2, so something must be improved, and we're going to look through that for an example. Oh, I should have pulled this chart up. Sorry about that. So as you can see, you have type A device in low demand mode. You have safe failure fraction of 0 with no redundancy, so you're only going to meet a SIL 1. So how can you make it to SIL 2? Well, one of the options, this is Route 2H for type A low demand mode application. We're also going to look at other ways to improve that in our example. And this is the type B safe failure fraction chart. As you can see, for type B, less than 60% safe failure fraction with no redundancy is just simply not allowed. So everything is shifted down and over one slot. Next, we're going to look at how to establish systematic capability. And the equipment used to implement any safety function must be designed using procedures intended to prevent systematic design errors. The rigor of the required procedures is a function of a SIL level. So here again, we have the SIL charts that we talked about earlier. And you could start with your safety integrity level and find the probability of failure on demand for low demand applications, like we spoke, and figure out your risk reduction. Or here it is for your high or continuous mode applications. So to also to look at, and this kind of gives you an example, a visual example on what to expect. So in 61508, you have annex tables, and they have a technical or description or a measurement. And as you can see here, you have recommended and highly recommended. And all these number measurements are requirements. You don't get to pick and choose. You can't say, oh, I want 1 and 3B. I'm not going to worry about 2 and 3C. It doesn't work that way. You have to meet all of these measurements, and that's what we talked about the on-site audit doing and the quality procedures looking at. So we would go in and make sure that you're making strides and you are doing all of the requirements per IEC 61508. So for complete compliance, once again, here is the certificate that we looked at earlier. As you can see, now that you know a little bit more, we're going to break this apart. In the white section in the middle, you see systematic capability, SIL 3 capable. So you know their quality procedures met a SIL 3 level. Great. Random capability, you can see this is a type B element. Okay, you now know that it is a smart device. And you can see here, SIL 2 at hardware fault tolerance 0, or SIL 3 at hardware fault tolerance 1, using route 1H. So that means that they use the safe failure fraction. Once again, you have to meet all 3 of these circles to be fully compliant. You can't just pick and choose 1 or 2 of these. So this little white section, once again, you have your SIL 3 capable. But you look to see the fine print. Well, it's not really fine print. It's large on the certificate, but it's smaller than the other print. It reminds you that you have to look at the PFD average and architectural constraints for complete compliance. So let's look at an example. I did this earlier in our Excellentia software. So I used a sensor, a logic solver, and a final element to make a system. I'm going to go ahead and blow up that bottom portion here. As you can see, we have an achieved safety integrity level of 2. Well, let's look at details. Why is this? Let's first look at your PFD average, the whole all the way over on the bottom to the left. You have your sensor and logic solver both meeting SIL 3, but your final element is only meeting a SIL 2. So because of that, you can only claim a SIL 2 on your PDF average. Okay, so we have the first PFD average component as a SIL 2. Now let's look at architectural constraints. The sensor architecture met a SIL 2, your logic solver architecture met a SIL 3, and your final element architecture met a SIL 2. Once again, you can't say you're SIL 3 even though one of them met SIL 3. You have to pick your lowest out of that for your safety integrity level. So once again, you have 2, 3, 2. You're going to have to pick a SIL 2 for your architectural constraint. Now let's look at systematic capability. For all 3, the sensor, the logic solver, and the final elements, you have SIL 3. Great. So can I claim SIL 3? You can say it's SIL 3 capable, but you cannot say that your system is a SIL 3 system because you have SIL 2 with your PFD average, SIL 2 with your architectural constraints. You have to, once again, pick the lowest number that you have. So your achieved safety integrity level is a SIL 2. So a lot of people ask us, how can I improve my safety integrity level? we're going to come back to this good old chart here. Once again, to be compliant, you need to meet all three: the SIL capability, the architectural constraints, and the probability of failure. So, to improve that, you're going to pick whichever one you're struggling in. You can improve your SIL capability, you can improve your architectural constraints, or improve your PFD average. So whichever you're a SIL 1 or a SIL 2 in and you want to be to the next level, you pick that category and you improve that category or categories. So if you want to improve your SIL capability, you improve the effectiveness of your internal quality management system. If you want to improve your architectural constraints, you can become a 1 out of 2, or you can be a 2 out of 3 system, or you can change your hardware fault tolerance from 0 to 1 or 1 to 2. Next, if you want to improve your PFD average, if you think back to the calculation, what were the main pieces of information in that calculation? You can decrease your proof test interval. You can decrease your mission time. You can change your architecture to 1 out of 2 or 2 out of 3, or you can revise your proof test coverage. And all of those will, a few of those will dramatically change your PFD average, but you can play around with a different combination to get to the PFD average that you need to be at. So I was bad and did not check the questions throughout my webinar. I'm sorry about that, but I will go ahead and look through the questions now. The first question that we received is, some customers forgo the systematic capability if the SIF is over-designed for risk reduction factor. Is that acceptable? We would, at exida, would say no. We would say that, yes, we are a conservative company, but we want to make sure that if lives are at stake, conservative is a good thing to be. So yes, we are happy when we see a SIF is over designed, but we still demand that systematic capability is looked at. The next question is, how does systematic capability get calculated or be established for a proven in use device? Also, do all certified products come with a safety manual? Yes. First, to answer the easy one, yes, all certified products do come with a safety manual. A part of the exida certification process, we demand that a safety manual is made available. They don't necessarily need to print out a safety manual and ship it in a box, but it needs to be on your website where your customers can access it easily. So yes, safety manuals, because it covers a lot of material. So if it is used in functional safety and is SIL rated, it must have a safety manual that you can easily find. So for the first part of the question, how does the systematic capability get calculated or established for a proven in use device? For proven in use, we have internal calculations and a database and spreadsheets that we use here. Also, systematic capability gets checked off the list of requirements that the list of requirements that IEC 61508 gives. So that is how systematic capability gets calculated, through the requirements of the standards and the checklists that we have along with our database. And proven in use is calculated from shipments and field failure numbers. The next question is Root 2H the same as proven in use? It is very similar. Route 2H is kind of proven in use on steroids. Route 2H is broken down in component level. So just like we do with the FAMITA, is this bolt or this nut proven in use? Do we have enough hours to claim this as proven in use? So yes, it is the same concept, but it is a more broken down, and the number is much greater. So we are comprised a database of different components that are used in many industries to talk to compile that number. So we have our database that I have compiled to make the 2H claim, because not one valve type or one actuator type would be making this 2H on its own, or one company on its own. Would you please explain the differences between the 2000 and 2010? I'm assuming you're talking about the safe failure fraction calculations with the number. The 2000 version of the standards allowed no effect failures, failures that do not consider safe and prevent the failure from happening, but also do not cause a failure from happening. So it just doesn't matter. So these no effect failures in the 2000 version of the standard were allowed to be up in the numerator of the safe failure fraction, or added to the safe failures. In the 2010 version, they took out that, and only safe failures are allowed in the numerator. So this is fine with type B or smart devices. They are still able to achieve a fine safe failure fraction. But with simple mechanical devices such as a valve, you now all of a sudden have problems. A valve, it simply does not have a way to have safe failures. It's a simple mechanical device. So all of a sudden, your safe failure fraction is 0. And they introduced Rail 2H as the clause to help mechanical components or mechanical devices out. The next question is, how does the probability relate to the time, like year? The probability, I'm assuming that we're talking about the probability, the PFD average, or the probability of, actually, do you mean the, I'm going to need a little more information on that one before I answer it, because we could be, I didn't check this at the time it was sent, I'm sorry. So if you still need the question answered after we have talked about it a little bit more, please supply a little more information on your question. I'm sorry. The next question, for a load demand, the risk reduction factor equal to 1 divided by the PFD average. So how do you obtain the risk reduction for high demand applications? That equation is in the standard, and it's one of the tables that we showed earlier. If we need that, again, I can send that out if you have further questions. If you need to see that table, I can send that to you if you'd like me to email that to you. Well, those are all the questions we have for right now. If you think of other questions, please email me. Please feel free to email me, and I will answer them as soon as I can. I hope that everybody has a wonderful evening or morning, depending on the time of day you're listening to this.